Welcome back to another exciting episode of Decentralized Application Development Crashcasts. I'm Sheila, and as always, I'm joined by the brilliant Victor. Before we dive in, I want to remind our listeners that your support means the world to us. If you're enjoying the show, please take a moment to rate us on your favorite podcast platform. It really helps us reach more developers like you.
Absolutely, Sheila. Every rating helps us grow this community of decentralized app enthusiasts. And speaking of growth, we're continuing our journey through the Hypercore protocol today, aren't we?
That's right, Victor. We're in Season 2, Chapter 3, and today we're exploring the fascinating world of data structures in Hypercore. But before we get into the nitty-gritty, I've got a brain teaser for our listeners. Here's the quiz question. What type of tree structure, commonly used in distributed systems like Bitcoin and Git, allows for efficient and secure verification of large data structures?
Ooh, that's a great question, Sheila. It's definitely something that's crucial in the world of decentralized systems. Without giving away the answer, I can say that this structure is named after a mathematician and is incredibly useful for ensuring data integrity. Listeners, keep this question in mind as we go through today's episode. The answer might just reveal itself.
Excellent, Victor. Now, let's start by recapping some key terms. In our last episode, we discussed append-only logs. Can you quickly remind our listeners what those are?
Certainly. An append-only log is a data structure where new data can only be added to the end of the log. It's like a book where you can only write new chapters at the end, never modifying or deleting previous entries. This property makes it ideal for maintaining a consistent history of changes.
Thanks, Victor. Now let's dive into today's topic. Can you explain what data structures are used in Hypercore?
Of course, Sheila. At its core, pun intended, Hypercore uses two main data structures: feeds and data blocks. A feed is essentially a sequence of data blocks. Each block contains a piece of data, and these blocks are cryptographically linked together to form the feed.
Interesting. So, if I understand correctly, it's like a chain of data pieces, each connected to the next. But how does this differ from a simple linked list?
Great question. While it is similar to a linked list in that each piece points to the next, Hypercore's structure is more sophisticated. It uses what we call a Merkle tree to organize these blocks. This tree structure is what gives Hypercore its power in terms of verification and synchronization.
A Merkle tree? That sounds intriguing. Can you break that down for our listeners?
Absolutely. A Merkle tree, named after Ralph Merkle, is a tree in which every leaf node is labeled with the hash of a data block, and every non-leaf node is labeled with the cryptographic hash of the labels of its child nodes. It's like a family tree, but instead of names, we use cryptographic hashes.
That's fascinating. It reminds me of those Russian nesting dolls, where each doll contains a smaller one inside. Is that a fair analogy?
That's a clever analogy, Sheila. It's similar in the sense of nesting, but with a crucial difference. In a Merkle tree, each doll, or node, doesn't just contain the smaller ones, it also holds a unique fingerprint, hash, of all the dolls inside it. This property is what makes Merkle trees so powerful for verification.
I see. So how does this tree structure benefit Hypercore specifically?
Great question. The Merkle tree structure in Hypercore allows for efficient and secure verification of data. When you receive a piece of data, you can verify its integrity and position in the feed without needing to download the entire dataset. This is crucial for P2P systems, where you might be getting data from multiple sources.
That sounds incredibly useful for decentralized systems. Are there any potential downsides or challenges to using this structure?
While Merkle trees are powerful, they do come with some trade-offs. One challenge is that as the tree grows, the verification process can become more complex. Also, managing updates to the tree structure can be tricky, especially in a distributed environment where different peers might have different versions of the data.
Interesting. How does Hypercore handle these challenges?
Hypercore addresses these issues through clever design choices. For example, it uses a flat tree structure, which simplifies certain operations. It also employs techniques like sparse replication, allowing peers to download only the parts of the feed they're interested in, rather than the entire dataset.
That's really smart. Now, I'm curious. How does this compare to other systems? For instance, how is Hypercore's use of Merkle trees different from how they're used in blockchain technologies?
Excellent question. While both Hypercore and blockchain technologies like Bitcoin use Merkle trees, they use them for slightly different purposes. In Bitcoin, Merkle trees are primarily used to efficiently summarize all the transactions in a block. In Hypercore, they're used to verify the integrity and ordering of data in a feed. Hypercore's approach is more focused on efficient data synchronization in a peer-to-peer network, while blockchain Merkle trees are more about creating a tamper-evident record of transactions.
That's a helpful comparison, Victor. As we're nearing the end of our episode, I think it's time to reveal the answer to our quiz question. The tree structure we were asking about is indeed the Merkle tree. It's amazing how such a fundamental concept plays such a crucial role in modern distributed systems.
Absolutely, Sheila. And for our listeners who want to remember this, here's a little mnemonic. Merkle's tree verifies with glee in Bitcoin, Git, and Hypercore's spree. It might be a bit silly, but it helps remember where Merkle trees are commonly used.
I love it, Victor. To wrap up, let's summarize the key points we've covered today. We discussed how Hypercore uses feeds and data blocks as its primary data structures. These are organized into a Merkle tree, which allows for efficient verification and synchronization of data in a peer-to-peer network. The Merkle tree structure is crucial for maintaining data integrity and enabling sparse replication in Hypercore.
That's a great summary, Sheila. Understanding these data structures is fundamental to grasping how Hypercore operates and why it's so effective for decentralized applications.
Absolutely, Victor. And to our amazing listeners, thank you for joining us on this deep dive into Hypercore's data structures. If you found this episode helpful, please remember to rate us on your podcast platform. And don't forget to visit crashcasts.com, join our Discord community, or support us on Patreon. Your engagement truly keeps us going. Until next time, keep exploring the fascinating world of decentralized development.